nanoHUB-U online instruction.
Hello and welcome back to nanoHUB-U's Introduction to Bioelectricity. I'm Professor Pedro Rithoki, and we are in week 6, lecture 4, solving Hodgkin-Huxley. So in this unit, we have been talking about numerical methods of solving differential equations. We began by talking about what is the difference between a discrete time versus a continuous time solution, and then we went into specific ways of solving differential equations using discrete time methods. First, we talked about Euler, then we talked about the sources of error in Euler and how we can do better with Taylor, but Taylor introduces more calculus, which is the whole reason for doing numerical methods, is to get around that because some equations cannot be solved continuously in the analytical domain. So we then introduced the Runge-Kutta, which gives us some of the accuracy of Taylor without the complexity of Taylor. It's the best of both worlds. And we talked about the different orders of Runge-Kutta, the fourth order being the sweet spot between accuracy and complexity. And we went through and looked at the process for solving a system of second order differential equations reduced to first order differential equations using a fourth order Runge-Kutta method. That was in the last lecture. What I want to do in this lecture is I want to talk specifically about Hodgkin-Huxley, and I want to teach you how to go about solving the Hodgkin-Huxley equation that we derived in the fourth module using a numerical method, specifically the Runge-Kutta fourth order. So we're going to go back to the Hodgkin-Huxley model. This is the equivalent circuit that we developed, and then we're going to take the equation that went with that equivalent circuit, and we're going to solve it in this discrete time domain. So you're going to get plots of action potentials from a simulated neuron. And that should be very rewarding. So the first thing to do is to go back to the literature. Hodgkin and Huxley did all of this work back in the early 1950s at the University of Cambridge in the UK. Actually, they were down in the southern England by the coast where they could get their hands on some giant squid axons to do their experiments. But they were both professors at the University of Cambridge in the UK when they wrote and published this paper. This paper went on to win them a Nobel Prize. The paper is a quantitative description of membrane current and its application to conduction and excitation in nerve. I encourage you, consider it required reading for the course, to go and download a copy of that paper. It's freely available all over the web. Just Google the title and you'll find that paper. Download it and read it. It's a fabulous paper. It's got over 16,000 citations. It's transformed our understanding of the modeling and behavior of electrical activity in sickle cells. It led, as I mentioned, to the Nobel Prize, and it's actually very, very well written. It's back when people used to write long-form, well-explained papers before they got into the habit of just writing large quantities of papers that were not always so coherent individually. Download it, go read it. It is the paper that you'll use to solve the Hodgkin-Huxley equation in this course. So in that paper, you're going to find the equation for two ways of solving Hodgkin-Huxley. The first one is the membrane action potential, which relates the membrane current J sub n, m, to the sum of the currents in the capacitive and resistive branches of the equivalent circuit. The second one is equation 30 in the paper, propagated action potential, which is what we call the Hodgkin-Huxley equation. It's what relates the membrane voltage, or the second derivative of the membrane voltage, with respect to time to the sum of the currents in the membrane. So one gives you the relationship between membrane voltage, which is in the capacitive current term, the derivative of Vm with respect to t, and the current and the sum of the currents. The other one gives you the relationship between those currents and a moving voltage. So a voltage that is moving at a constant velocity v, given here. So v is what allowed us to switch, if you recall, from week 4, it's what allowed us to switch from the time space domain to the time domain to get a homogeneous ordinary differential equation. So we have these two equations. In this course, what we're going to do is we're going to solve equation 26, the membrane action potential. They're both good equations. It's not that one is better than the other. It's that you solve them in different situations depending what you're trying to get at. So if you recall from earlier in the semester, we talked about electrically large cells and we talked about electrically small cells. In an electrically large cell, the voltage at one point in the cell can be different from the voltages at other points of the cells. So if you create a voltage in one place, it's going to propagate. It's going to diffuse out along the cell, and so that signal is going to move along the cell. If you want to be able to model the relationship between the membrane voltage and the current in an electrically large cell like this, you have to use the Hodgkin-Huxley equation for propagated potentials. In an electrically small cell, the voltage at any point in the cell is assumed to be equivalent to the voltage everywhere else because the cell is so small there really isn't enough room to have a difference in potential in one place to the other. In an electrically small cell, you can use the membrane action potential to model the electrical relationship between the membrane voltage and the current in that cell. So you can use different equations depending on whether you're looking at large cells or small cells. And for this course, we're going to look at small cells and we're going to solve the membrane action potential equation. So to solve that equation is equation number 26 in the journal paper. So get that paper, and all of the equations that I'm going to reference and all the page numbers I'm going to reference, they're all from that paper. So get that paper, and this is the equation that we're going to solve. We can rearrange this equation 26 so that it is in terms of the membrane voltage with respect to time. And that's just by switching terms over from one side to the other side of the equation. So the membrane voltage with respect to time is going to be equal to 1 over the capacitance of the membrane multiplied by Jm, which is the current through the membrane, minus Gk bar times n to the fourth times the difference between the membrane voltage and the resting potential for potassium. That's the potassium current term, plus Gna times m cubed h times the difference between the membrane voltage and the resting potential for sodium. That's the sodium current term, plus the leakage current term. So these current terms are all going to be summed up, and you add the membrane voltage, or you subtract them from the membrane voltage, you divide it all by the capacitance of the membrane, and you have the derivative of the membrane voltage with respect to time in an electrically small cell, and only in an electrically small cell. So this equation has 4 unknowns. The membrane current, Jm, which we don't know, M, N, and H. Now M, N, and H were all solved by Hodgkin and Huxley. So the first equation, U1, we're trying to reduce this system to this equation to a system of first order ordinary differential equations. We already have one. That's equation 26, the one relating the membrane voltage with respect to time to all of those other variables. But we need 3 more equations because we have 4 unknowns. We need 4 equations, and those equations need to relate N, M, and T to the other variables that we have. So the second equation is going to be equation 7 from Hodgkin and Huxley, which is the one that defines the variable N. And remember, N, M, and H were not derived. They don't have a basis and an understanding of the physiology of the neuron. They are curve fits. They are equations that are invented to solve the problem. So they were determined empirically. They did a series of measurements, and based on their measurements, they derived or they wrote down equations that would fit the curve of what they had actually observed. And so this is equation 7 in their paper, which describes the relationship with the variable between the variable n and these 2 variables alpha and beta. And then there's equation 15 and equation 16, which do the same thing for m and h respectively. And then we can go in and look at equations 12 and 13 in the Hodgkin-Huxley paper, which tell us what alpha n and beta n are, the 2 variables we need to solve for n, and they're both a function of the membrane voltage, Vm. From equations 20 and 21, we have alpha m as in Mary and beta m as in Mary, which allow us to solve for m. In the Hodgkin-Huxley equation, we have equations 23 and 24 in the paper, which allow us to do the same thing for h. So given all of these equations from the paper, which you can enter in to the program that you're going to be writing, we'll talk about that in the next lecture, you can then write everything down so you have 4 ordinary differential equations. And there are a series of constants that come up. There's Gk bar, Gna bar, Gl, Vk, the resting potential for potassium, Vna, the resting potential for sodium, Vl, the leakage resting potential, and the membrane capacitance. And all of these are given in the paper. They were all determined experimentally by Hodgkin and Huxley in the early 1950s. So you can find them on page 520 of the paper. And then one critical note. Throughout this course, as is common in textbooks and in papers today, we define the membrane voltage as the difference between the voltage inside the cell and the voltage outside the cell. And so the voltage inside the cell is more negative than the voltage outside the cell, so the membrane voltage is negative. Typically, it's about minus 65 millivolts. Hodgkin and Huxley defined it the other way around. There isn't a right way or wrong way, they just did it the other way. And so when you go through the paper, if you go and you solve everything, you're going to end up with action potentials that are upside down. And the reason for that is because they define the membrane voltage in that way. And all of the equations in the paper are defined in that way. So rather than having to refigure out all the equations with the other polarity, don't worry about it. When you get to the end and you solve for the membrane voltage, just multiply it by -1. Flip it. And then it'll come out the way you would expect to see it, the way that we define membrane voltage now and the way we've done it in this course. So again, we have 4 equations, and we're going to define them as U1 prime, U1, U2, U3, and U4. Those are our 4 variables, Vm, N, M, and H. And then we have the equations which relate the first derivatives of each of those variables to the other variables. So U1 prime, which is equivalent to Vm prime, is going to be equal to 1 over Cm times Jm, the membrane current, minus the product of all the other currents, the resistive currents in the cell. Then we have U2 prime, which is going to relate N to alpha N and beta N. You have U3 prime, which is going to relate M to alpha M and beta M. You have U4 prime, which is going to relate H to alpha H and beta H. And then you have an initial condition. If you're providing a current stimulus, that initial condition is going to be that current stimulus. Or if you're providing a membrane voltage stimulus, then that condition is going to be that. So initially the cell is resting, right? Nothing is going on. So the membrane voltage is going to be 0 and the membrane current is going to be 0. So the initial conditions are Vm is equal to 0 and Jm is equal to 0. Easy enough. But if you leave them at 0, then the cell is just going to sit there and it's going to do nothing. If you want to get the cell to fire an action potential, then you need to stimulate it. And the way we model that stimulus, which we referred to in week 3 and week 4 as KE, the way we apply KE is either through a voltage, which is equivalent to a postsynaptic potential, or through a current, which is equivalent to a stimulating electrode applying a current. So what you'll do in your program is your default will be to set Vm to 0 and Jm to 0, but then you'll decide which sort of stimulus, or rather you'll ask the user what sort of stimulus they want to use, and then you'll either, if they want to use a postsynaptic potential stimulus, you'll set Vm to be non-zero, say 20 millivolts initially, or you'll set Jm to be non-zero for the width, the amount of time that is equivalent to the current pulse that you want to deliver. And all of this will become clearer in the next lecture as we start going through the code that you're going to be writing. But you can set these values and then you can play around with them and you can do things like set the membrane voltage to just 5 millivolts and see, does that give you an action potential? And it won't. If you do 20 millivolts, it will. So at what point does it start giving you an action potential? And that point is the threshold voltage that we talked about in week 4 when we were going through the Hodgkin-Huxley equation. So it's really cool. Once you have all this coded in, you can really go in and start playing around with the neuron and seeing how the neuron responds to different sorts of stimuli. But for starters, you need to write all of the code. So you'll have your initial conditions, you'll have your 4 equations, and then you'll go through and you'll use the 4th order Runge-Kutta approximation. So your initial values will be set for each of the variables Vm, M, N, and H. And those initial values, the initial value for Vm is Vm naught, which is 0 unless you're using a postsynaptic potential, in which case it's non-zero. And the initial value for N, M, and H are given by the equations for N, M, and H, which are all in the Hodgkin-Huxley paper. And you can calculate N, M, and H from their alpha and beta values. So you can plug the equations that we showed in the previous slides. You can plug in those initial values and you can get what the initial conditions are for each of those equations. And once you have the initial conditions, then you can start doing your 4th order solution using Runge-Kutta. So you're going to solve Runge-Kutta for n points, capital N, from 0 to n minus 1. And you're going to do this for 4 first order equations. So capital M, which is the number of equations, is 4, and it goes from 1 to capital M, which is 4. Here it's U1 to U4, where U1 again represents the membrane voltage, U2 is the variable N, the U3 is the cat variable M, and U4 is the cat variable H, where N is used to solve for the potassium current, and M and H are used to solve for the sodium current. So when you're done with all this, you're going to have a solution for the membrane voltage, but you're also going to have a solution for N, M, and H. And you can use those. You can use N to not just you use Vm to plot Vm, so you'll see that action potential response, but then you'll use N to plot the potassium current. So you'll know what the potassium current is at every point in time as well, not just the membrane voltage. And you'll use M and H to plot the sodium current. So you'll know what the sodium current is too. So you'll know what the transient outward currents are. You'll know what the delayed inward currents are. You'll know what the membrane voltage. You'll know everything about what's going on electrically in the cell. And you'll know it just as it's happening. And it'll plot it out. It'll be really nice. So the first step is to do the Runge-Kutta. And the first step is to calculate the first slope at the first point for all of the equations. So we have the starting conditions. That's n equal 0. Now we're going to calculate it at n equals 1. That's the first unknown point. So slope 1 at n equals 1 for u1, which is Vm, is going to be a function of t, the point in time at which you're at, and what the current values are of u1, u2, u3, and u4, where we're using big U as the function and little u's as the specific value of that variable at that point in time. And so we're going to calculate k11, the first slope for the first point, the first equation. We're going to calculate k12, the first slope at the first point for the second equation, k113, the first point, the first slope, the third equation, k114 is the first slope, the first point, the fourth equation. And when we're done, we'll have the first slope for the first point for all four equations. And then we need the second slope, the one that we calculate at the midpoint. So the first slope is calculated at the beginning, the second slope at the midpoint, the third slope at the midpoint using the second slope, and the fourth slope at the end point using the third slope. So we use the previous slope each time we calculate the next slope, and we do it at different points for the first slope, the second and third slopes, and the fourth slope. So calculating the second point slope, we use the values that we had for the first slope to get to the midpoint, and we calculate that slope at the midpoint. So we do the second slope at the first point for the first equation, k211, the second slope still at the first point for the second equation, k212, the second slope, first point, third equation, k213, and the second slope still at the first point, fourth equation, k214. And they're all evaluated at the same point, but they're different equations, u1, u2, or different functions, u1, u2, u3, and u4, that you're evaluating at that point. Once you've done that, you move on to the third slope. The third slope, k3 at the first point, k31 for the first equation, k311. The third slope, first point, second equation, k312. The third slope, first point, third equation, k313. The third slope, first point, fourth equation, k314. That's also calculated at the midpoint, but it's different from the second slope because we're using the second slope to calculate it, whereas for the second slope, we use the first slope to calculate it. Then we move on to calculating the fourth slope. And the fourth slope is calculated at the end point. And you can see that here when we're evaluating, we're not multiplying h over 2, we're multiplying h times the third slopes. So we're going to calculate first the fourth slope for the first point for the first equation, k411, the fourth slope for the first point for the second equation, k412, the fourth slope for the first point for the third equation, k413, the fourth slope for the first point for the fourth equation, k414. Now we have all four slopes for all four equations, all at the first point. Then we can take the weighted average of all those slopes, where k11 bar is the average slope at the first point for the first equation. And it is equal to 1 over 6 times k111 plus 2 times k211 plus 2 times k311 plus k411. So it's the weighted average of the first, second, third, and fourth slopes at the first point for the first equation. Then we calculate k21 bar, or k12 bar, which is the average slope at the first point for the second equation, and that's the weighted average of the first, second, third, and fourth slopes at the first point for the second equation. And then we calculate k13 bar, which is the average slope at the first point for the third equation, is the weighted average of all four slopes at the first point for the third equation. And then finally, we solve the average k14 bar slope, which is the weighted average at the first point for the fourth equation of the four slopes we had for that equation. Now we have all of the slopes, the average slopes, and we can use something that looks a lot like Euler to solve for the second point, which is step 6. U sub n plus 1, comma m, where m is the equation number, and u21, which is the second point for the first equation is going to be equal to U11, the first point for the first equation, plus h, which is the distance between the current point and the second point, the first point and the second point, multiplied times the weighted average slope, K11 bar, for the first point for the first equation. U22, the second point for the second equation, is going to be equal to U12, the first point for the second equation, plus h times the average slope for the first point for the second equation, K12 bar. And the same thing for U3, and the same thing for U4. So once you've gone through all this, you're basically done. You've solved, knowing what the initial conditions are, you've solved for the next point, for the Hodgkin-Huxley equation. You've done it for Vm, you've done it for N, M, and H, which allow you to know what the ionic currents are, and you've done it for the next point. To do the point after that, all you have to do is write a for loop around everything you just coded and run that for loop as many points as you want. In this case, capital N minus 1 times. And when you do all of that, you'll be able to extract the membrane voltage, where the membrane voltage is equal to U little n, comma 1 for the first equation, as little n goes from 0 to capital N minus 1. And you'll be able to extract the potassium current, because the potassium current is just GK bar times U2. And you'll be able to extract the sodium current, because the sodium current is just GNA bar times U3 and U4, where U3 is cubed and U4 is to the first power, because it's M cubed H. For the potassium current, it was U2 to the fourth power, because it was N to the fourth power times GK bar. So you'll be able to use those Hodgkin-Huxley equations again from the paper to extract the membrane voltage, the potassium current, and the sodium current. You'll have all of your values. And once you have those values, you can plot them. And so here's a plot. I wrote the program, and I did it in Python just as you will. And in Python, you can solve and you can plot. And here's a plot in red of the membrane voltage as a function of time when I provide a voltage stimulus. So there's a voltage stimulus. This voltage stimulus, as you can see, is enough to trigger an action potential. You have a rising phase, you have a falling phase, you have an undershoot, and then you have a long and gradual recovery. That's the membrane voltage. And at the same time as the membrane voltage, you can plot the transient inward sodium current here in blue, and you can plot the delayed outward potassium current here in green. So you can see those ionic currents. You can see how they add up to the membrane voltage, where keep in mind that the potassium current would actually be flipped on the axis, or the sodium. They would be flipped with respect to one another. We've drawn them both here positive because they're both positive currents, but they point in opposite directions. So in order to get the voltage response that you would see, you would actually want to take one of those two. Doesn't matter which one, depends on how you define your membrane voltage, inside to outside like we do, or outside to inside as Hodgkin and Huxley do, and then you would get the waveform shape that you would expect to see. So this is what you would get for a voltage stimulus. You can also do a current stimulus, and if you do a current stimulus, in this case, we have a current pulse that begins at this point in time, and it goes negative, and then it stays negative for a little while, and then it goes positive again, and this current pulse causes a depolarization in the membrane, and that depolarization is the integral of that current, so it's a rising slope until you hit that threshold voltage, and when you hit that threshold voltage, you get a rising as you get a transient inward current of sodium ions, then you get a falling edge as you get a delayed outward current of potassium ions before you restore back to the resting membrane potential. So it's everything that we've learned in the semester leading up to this equation. And then rather than having to take my word that this equation actually models action potentials in neurons, you'll be able to code it and you'll be able to see for yourself that you can solve this equation in real time, and that the solution to the equation will allow you to predict all of those things that we talked about in lectures 4.4 and 4.5. You can see them all here in your own handiwork. So in the next lecture, we'll come back and we'll go into Python, and we'll talk about how in Python, which is freely available, open source, and so on, so you can install it on any computer and you can use it without a license, without spending a nickel. In Python, you can write the code that'll give you the plot that I just showed you here and allow you to do all of this on your own computer. And I'll see you then.